Emily, once you get that started, can you go get the quizzes? Yeah. Welcome back. How was your weekend?
It was good.
Good.
How was yours?
Pretty good. I did not. I did.
Green.
I am wearing green. That's hence the outfit that you approved. I did defend my number one disc golf tag against like 10 people, and I won by like 8 points, 8 strokes.
Is that pretty good then?
Yeah, I played really well. I was really a little bit of both. Kylie?
Sydney's not going to be until like 11:20 because she has.
Okay. Gotcha. Luke? This is the old ones. I just been carrying them around, and I figured it's a good time to give them back. And then this is the attendance sheet.
Yeah.
All right, we're going to cover a little bit of new stuff, and then we're going to have a quiz. And then on Wednesday, we're going to do some fun, like really fun demos on something called Lenz's Law, which explains, 1, how we can generate electricity, and 2, how we can use magnetic fields for things like brakes on roller coasters and trains. Yeah.
So, first,
Okay.
are we using the, are there going to be the ones with the wires that we equation?
You mean with the 2 wires?
Yeah, with the current and then the length.
Oh, that equation.
Okay,
It's the so those 2 equations are like the same equation. All right, marker. Thank you. F equals QVB sine theta, and F equals ILB. The murmur is a little distracting. So the murmur's got to stop, or I can't focus. All right, that's better. Those 2 equations, those are actually the same equation.
Yeah. And then
But-
there's the one where we did where we put the mass and velocity squared over R. Why did you put that for the 4?
Oh, okay, that's not on the quiz, but it's still something worth knowing, because have you ever heard of a mass spectrometer? That's how they work, which is kind of neat. I'm going to do that one over here. We had a charged particle. It was going to be moving through a field, and it was going to feel a force. So it's moving this way. It's going to feel a force that way, which is going to make it go in a curved pattern. So let's say I'm just shooting it out, and then I've got a sensor here. It's going to follow a curved pattern because the force is down. Its velocity is this way. And we got a B field coming out of the board. B field coming out of the board, right? You're going to feel a force down. You got that? So anytime you have a force perpendicular to the direction you're moving, you're going to follow a circular path. And if you can measure how far this is, you can figure out how much mass it has based on the way we did that problem. Because it follows the circular pattern. When you have a circular pattern from Physics 1, Dr. Jones, I know she taught you this, it follows centripetal force rules. F sub C equals mv squared over r. That's, no, it's just how this mass spectrometer works. So not on the quiz, but it's just, you needed it for the homework, and we used it for that homework problem. And she asked about it.
When there's like certain questions you have to stuff that, is there like a certain phrase that you want to use that, or just like the?
If it's following a circular path,
Okay.
centripetal means towards the middle, literally, but it's for uniform circular motion. I don't remember what chapter that is, but it was from Physics 1. And that's for anything. You could have it in friction, you could have it in gravity, you could have it in electromagnetism. Anytime you got something going in a circle, it's going to have some sort of centripetal force. Next time you're at an amusement park, on a roller coaster going around a curve, you can think about that equation right there. When you're in a car going over a hill too fast and you kind of lose your stomach, it's because of that equation right there. Because gravity is providing the centripetal force to make you go around this curve, and gravity didn't provide enough, so you end up in free fall, which is kind of cool. I love physics. Like, literally everything that there is fits in some category somewhere. Water polo, all kinds of circles in water polo. You don't swim in a circle too much. Is that a thing?
That's how you, like, that's a kick that we use when we tread the water.
Oh.
Because you don't touch the bottom of the floor. Like,
Yeah. Yeah, your sport is wild because it's just constantly trying not to drown. Like that's the entirety of your sport. Okay, so back onto the topic. You asked about those equations. I think I answered that. You asked about that equation. I think I answered that. This is pretty important, so make sure you're paying attention. So I went through the plan. The plan today, we're going to cover a couple new things, and then we're going to get you your quiz. We're going to finish those new things and give you some really cool demos on Wednesday. On Friday, I'm going to be in Philadelphia for my grant, my research grant. I got to be there for a presentation. One of our teachers in the research grant's it's kind of cool, getting a national award, Teacher of the Year, like nomination, Teacher of the Year nationally. So I've got to be there for that. So I'm going to make a video like I did last time. You're going to watch that video, and it's going to have information about generators and transformers. And to head off your question and at the pass, yes, that is viable for the exam. We have an exam scheduled for before winter or Easter break.
It's Monday.
That would be Monday, yeah.
Oh boy.
If you are interested, I'm going to be driving, but I should be back by Sunday evening, and I can do a Zoom session if that's something you want to do. So I'll have to check the timing. I don't know exactly when I get back, but I will get back sometime Sunday. I could be. I mean, I have dreams about this physics stuff, so like we could have a review at any point in time. Yeah. Let me see if I can find one. They're saved all over the place. I'll see if I can find a good one. Maybe. Were her exams like mine? Well, then it wouldn't be helpful. I mean, I'm happy to do it, but I don't know how much use it would be for you.
Yeah. You can do practice problems on Sunday.
Oh, that's a good idea. You know where I stole a bunch of the test problems from, right? Your textbook and the homework. I mean, those are the same. The ones in your textbook are the ones that are in the homework, which are the ones I stole for the exam. I don't know. I haven't made the video yet. That one occurred to me because I wanted to do that with you guys, and since I wasn't here to do it with you guys, I wanted you guys to do it and have that experience.
Jumping back to the quiz, will there be anything on there where we have to draw like that wire and then the...
Always a good idea to draw stuff. Maybe, probably, possibly. I can tell you right now. So if it's drawing a magnetic field, we know they make closed loops. We know the stronger the field is, the closer together those loops are. The lines are going to follow the right-hand rule, the right-hand curl rule, where my finger goes in the direction of the current or the moving charge, whichever it might be. My fingers curl. For a positive charge, they don't curl this way unless they're broken. And that has happened in karate class, but not to me. So it's only going this way. So it has to go that way around.
I think I had the one kind of scary looking drawing with all the like tangential arrows.
I don't remember that one. Do you guys remember that one? I don't remember that one.
No one knows.
I'm not trying to be a jerk. I genuinely don't know which problem you're referring to. If you can find it in your notes and show me, then I can answer.
It's in the textbook. That must be it.
Okay. Yeah, if I don't know what you're talking about, then it's probably not something I wrote on the quiz. Okay, so new stuff. We know that moving charges produce magnetic fields. That's the only way a charge makes a magnetic field is by moving. If it's not moving, it doesn't make a magnetic field at all. So if I just have a positive charge just sitting here in space, It is affected by electric fields, but it's not affected by magnetic fields because it only produces a magnetic field when it moves. So it's the change that initiates the magnetic field. Does that make sense to you? So scientists in the early study of electromagnetism wanted to figure out if it could go the other way too. So we can create magnetic fields by moving charges. Could we use magnetic fields the other way? So could we make charges move using magnetic fields? So what they did was they hooked up a battery to a coil of wires to make this piece of iron, this iron ring, magnetized. And they wanted to see if they could produce a current on the other side. To move charges, produce a current using these magnetic fields. Because think about how powerful that is. If you can create current, you don't need a battery. You can generate power some other way. It's an alternate way of generating power besides this chemical means of having batteries that separate the charges and hook up. That thing, by the way, that has the coil of wire on one side and the coil of wire on the other and a piece of iron that's magnetized in the middle is called a transformer. And we're going to talk about that on Friday in a video. But just so you know, that's exactly what that is. So Faraday, I thought it was a different guy. I thought it was Ørsted, but Ørsted's experiment is the one with the two wires. Faraday did this. The same guy who Farads are named after, he did electric fields, Michael Faraday. He did this and nothing happened. Not a thing. He had the current going through the wire. That current made that piece of metal magnetized. Nothing. So in disgust, he turned it off and bam, he got a current. Only for an instant. When he turned it off, got a current. So he's like, whoa, I got a current, but it went away. So he plugged it back in. He got a current going the other way all of a sudden, and then it went off again. So what's going on here? As it turns out, it isn't a magnetic field that causes current to come to existence. We need a voltage for there to be a current. So the magnetic field itself doesn't create the current. It's a change in the magnetic field that produces a current. Just like only moving charges, which would be a changing electric field, causes magnetic fields. Changing magnetic fields produce voltages, produce these electric fields that move charges. In order to understand how this works, we need two new concepts. The first of those new concepts, I'm going to skip ahead, is called flux. Some people say no flux are given. I disagree. Flux is a term we use to describe how much of something is passing through a surface area. In this case, we're talking about magnetic flux, and that's how much of the magnetic field is pointing through a surface area. As you're writing this down, I have to grab something out of the lab. I'll be right back. Thank you for your patience. I have here a bed of nails. I also have a little loop of wire. If I want to talk about the flux of nails through the wire, all I'd have to do is figure out how big the wire is and how many nails go through it. Same thing for magnetic field. Magnetic flux is the amount of magnetic field lines that go through a given area of whatever it might be. Now, if I put the loop like this, so that the face of the loop is perpendicular to the direction of the nails, none of the nails go through. None of them. So 0 flux. If I want to maximize the amount of nails that make it through this loop, should I put it at some angle? What should I orient the loop to be? It should be horizontal, so that the face of the loop, if I was to make it flat, like if it was a piece of paper and I was reading it, would be pointing in the same direction as the direction the arrows are pointing. So there'd be 0 angle between the area vector of this and the direction of the nails. That means that I need a, why does it keep disappearing? That means I need a cosine term in there, which I have. That's this cosine term right there. B is the strength of the field. That's the number of field lines going through the area. A is the size of the area it's going through. And cosine is the angle between the area vector and the field. I think the drawing shows it about as well as I could say it. You have some area of some shape. You have some number of field lines represented by the B field. And you have some angle between those two things. Magnetic flux is measured in Webers, WB. Hi. Okay. Sorry you're hurt. Glad you're getting around. All right. So magnetic flux is represented by the Greek letter phi, PHI. It's like a capital letter I went off of its diet. I see you. You hold that question. Oh, tell me your fun fact.
That is the letter F in Ukrainian alphabet.
Really?
Yeah.
Is Ukrainian somehow related to Greek?
I'm not sure.
That's super interesting.
But do you want to know?
I just learned something. I know how to say hello in Ukrainian.
Starts with F, so maybe.
There you go. Privyet is hello. So you take a letter I, and then you take it off of its diet, so it gets kind of fat in the middle. And that's how you get a Greek letter capital phi. That's the symbol we use for flux. You can put a little subscript M if you want, but it's the only kind of flux that we're going to talk about in this chapter. Magnetic flux equals BA cosine theta. Capital letter H in the Ukrainian alphabet. I had no idea. F. Oh, F.
For flux.
You did say that, and I'm just not that smart. Good call. Thank you.
You're smart.
And that was kind of you to say too. I was being humble. Why is this important? Why do we care about the magnetic flux? Because the magnetic flux is how we measure the change in the magnetic field. By changing the magnetic flux, we induce an EMF. Do you remember what an EMF is? We only talked about it kind of briefly in class. It's just a fancy word for voltage. EMF is just a fancy word for voltage, but it's the one we use for this particular part of the chapter, for this particular part of the book. To induce an EMF, we look for changes in flux. You can change the flux by changing anything. You could change the strength of the magnetic field. You could change the area that's going through it, or this is what we normally do when we're generating power at our power plants in electric generators. You change the angle between them. By changing the angle, the area, or the strength of the field, you will generate some EMF. I can prove it too. But before I do, I'm going to give you the equation just because, you know, that's important. EMF equals negative N delta phi over delta T. The negative implies direction. We are going to talk about that next class. The N is the number of loops in your area, your coil. This flashlight has a coil of wire. This is a coil of wire. Every single one of those loops adds to the EMF generated, hence the need for a solenoid. If you have a single loop, your N is 1. If you have 100 loops, your N is 100. You get 100 times more EMF. Delta phi is your change in flux. Delta T is the change in time. I had a couple practice problems, but I want to get you going on your quiz right away. But I want to show you, I want to prove this, that it actually works. So I brought with me a amp meter. I brought with me a coil of wires hooked up to it. And I brought with me my strong magnets. If I just hold the magnets here, nothing really happens. Now, if you were paying really close attention, you saw that when I brought the magnet close, it wiggled. But when I just sit it here, nothing happens. If you guys want to come, get up here, come see it. Or just stay where you're at, don't bother. Okay, all right, fine. Only the change in flux matters. And how do I change the flux? I either change the strength of the field, the area, or the angle. Well, changing the area of this is not really possible. I'm not going to be able to stretch the wires or squeeze the wires because they're solid. This thing is really heavy. It's solid metal. I'm not going to be able to do that. But I can change the strength of the field by bringing the magnet closer and farther away. You know that the field is strongest near the pole of the magnet. So if I bring the pole of the magnet here, I get a current. If I pull it away, I get a current going the other way. I make the flux bigger, I get a current this way. I make the flux smaller, I get a current the other way. Any change in flux, if I drop this through there, I would get a spike, which is pretty awesome. The faster I do it, the bigger the spike. The slower I do it, because delta T, if delta T is big, the EMF is going to be smaller. I get a smaller spike. If I make the delta T small by making it fast, I get a bigger spike. Pretty cool, right? Now this, you ever see one of these flashlights that don't need a battery? It's got a magnet inside. It's not the copper wire. Copper doesn't stick to magnets. It's the magnet inside. You can hear it, right? There's a magnet inside doing exactly what I'm doing here. Changing the strength of the B field, which allows it to light up. The reason I bring this in and don't keep it in my car anymore is because the battery inside doesn't hold the charge. But you can see that it does work as it lights up. Kind of cool. That was dumb. All right, cool. That's foundational. We're going to do some practice problems and some demos next class. The